Hello everyone. So this side Dr. Nitin Sharma from IT department AKGEC. So today I am talking about a topic which is recurrence relation from the design and analysis of algorithm. So how do you trace a recursion relation? So as the name is already defined that what is recurrence relation, the function is calling itself. So that is called a recurrence relation. You can see the example here. So this is the function void test, and you can see inside this function, the function is again called with the value of n. There here is n minus 1. So it is recursively called. If I can check out through the recursion tree, so tree is that when the test 3 is calling, so 3 is given here and the test 2. That means n minus 1 is calling here. Again n minus 1 is calling here. So 2 minus 1 is 1, then minus 1 is 0. So 1, 1, 1, 1. The total call is 3 plus 1, 4 times. So this is the way the recursion is calling here. One more example you can see here. If I can draw an recurrence relation from this for this example. So this is the function which is basically the Tn, and this statement is executed only one time, and this is also executing in one time, but this is basically another function is calling that. Suppose this is Tn because the value is n here and here is a n minus 1. So this is Tn minus 1. So 1 plus 1. So that the function is Tn is equal to Tn minus 1 plus 2. Why it is 2? Because the two statements are already executed whenever the Tn function is calling here. So the recurrence relation you can see here. If n is equal to 0, then it return 1. If n is greater than 0, then the function is Tn minus 1 plus 1. This is the way you can just make a recurrence relation, and after that you can solve it. So you can see some recurrence relation here. I'll just give in some example. Tn is equal to Atn upon b plus fn. This is basically the basic format, and Tn is equal to Tn minus 1 plus n, Tn by 3 plus T2 n by 3 plus n. So this is the kind of recurrence relation you can see when you are trying to solve the recurrence relation. So some of the approach are basically used to solve the recurrence relation, that is iterative method, substitution method, regression tree, master theorem method. So today I am going to discuss one by one. Okay, so substitution method is, guess the form of the solution is given and you can just put it in one by one, and it is solved mathematically. Okay. So here this is the question here. Again the same recurrence relation I discussed earlier. Tn is equal to 1, Tn minus 1 plus 1 if n is greater than 0. How you can solve it? By the using of substitution method. So this is the solution. I'll explain you this line by line. So initially you can see that this is the equation, and if you are going to calculate the value of Tn minus 1, so what is this? On the basis of this, n minus 1 is equal to, so in this equation you can put n minus 1 in the place of n. So if I am putting here n minus 1, so here is t n minus 2 then plus 1. So this is the value of basically Tn minus 1. I can put this value here and you can see this is the value here. Okay. So when this value is putting here, the Tn is equal to Tn minus 1, 2 plus 2. Similarly, you can put the Tn minus 2 value. So this is the Tn minus 3 plus 1 plus 1. So the answer is Tn is equal to Tn minus 3 plus 3. So if you can observe here, when the function is calling first time, this is 1, second time n minus 2 plus 2, third time n minus 3 plus 3. So after kth step, the equation is basically created. Tn is equal to n minus k plus k after kth step, and at the kth step, this is basically the terminated. So when it is terminated, according to the function given here, when n is equal to 0 is 1. So whenever n is equal to 0, it is constant. So it will be terminated. So n minus k, we can put here n minus k is equal to 0. So the k is equal to n. Then we can put here, and you can see when Tn is equal to T0 plus k is equal to n, that means 1 plus n. So the big O of this is n. This is the solution of this. Okay. So this is the way you can solve the recurrence relation. One more example you can see here. So this is another example. I can just some changes here. In the place of 1, I can put here n. Similarly, we can put the value. So first time here equation is Tn is equal to Tn minus 1 plus n. Second time is Tn minus 2 plus n minus 1 plus n. Third time Tn minus 3, n minus 2, n minus 1, n. Okay. So after kth point, what will happen? Tn is equal to Tn minus k, Tn minus k minus 1, Tn minus k minus 2, and so on. till n. Okay. When it will be terminated? When this recursion function is terminated, right? So it will be terminated when n minus k is equal to 0. So n is equal to k. At this point, the recursion function is to be terminated. So I explain here. So when the value of k, I'll put it in this equation. So this is becoming a 1. Wait. Okay. So this is becoming a 1, 2, 3. So series is coming like 1, 2, 3 plus till n. What is this? This is basically a sigma n. And the value of sigma n is n into n plus 1 by 2. So Tn is equal to, when I am writing here, Tn is equal to 1 plus n into n plus 1 by 2. So what is the answer? Big O of n square. The highest power you have to be taken here as a complexity. Okay, and ignore the all other powers. One more example. Tn is equal to 1, Tn by 2 plus n. How it can be solved? Again, recursion. So in the place of Tn by 2, I can just put it here. The equation is Tn by 4 plus n by 2 plus n. Okay. Again, we have to put the Tn by 4 values. So Tn by 8, Tn by 8, n by 4, n by 2 plus 2. So this is the way the equation or the recurrence is occurring, and the equation is coming like this. Okay. So let's see. Tn is equal to, after the kth point, T n upon 2k, n upon 2k minus 1, n upon 2k minus 2. This is the way the series is here. When it will be terminated? When n upon 2 to the power k is equal to 1, it will be terminated because the value of T1 is 1. Because of T1 is 1. So this is the way you can calculate it here, and the k is equal to log 2n. This is the way you can just calculate it, the value of k, and now you can put the value of k inside the equation. So you can see this is becoming a 1 and n is common here, and this is the equation. And if I can value put it here, k is equal to log 2n, it is coming like 1 plus 1. So the final answer is Tn is equal to big O of n. Got my point? So this is the way you can solve the recurrence relation by using substitution method. This is another example you can do by yourself. Tn is equal to 2tn by 2 plus 17 plus n. What is recurrence tree method? Another way you can solve this kind of relation is recurrence tree method. Recurrence tree is each node represent a cost of single subproblem somewhere in the set of recursion function. Okay. So at the end you have to be sum the cost of each level, and after that you can get the final answer, how much time it will be executed. It will take the execution. Okay. So same question I can repeat it here by using the recurrence tree, right? So this is the same example. This is the recurrence tree. When Tn is calling, total n number of steps is running. Because why? Why? Because this is n. Okay, I told you in the initially, like whenever our recursion function is executed, how many elements are basically processed? So total n number of elements are processed, right? So this is basically n element are processed, nth element are coming here, and the Tn minus 1 are left. When this function is running, the total number of time is taken is n minus 1. Similarly, n minus 2n. So this is the way this is running till the 0. Here you can see some steps are occur until the 0. And if I can sum all of them, right? So it is basically 0 plus 1 plus 2 plus 3 and so on plus n minus 1 plus n, right? What is this? This is again sigma n. N is basically n plus 1 by 2. So big O of n square. Got my mind? One more example we can take here. Tn by 2 plus n. Okay. So how it can be solved? So Tn, when Tn is running, so here you can see n is the number when Tn function is calling, total n number of element is processed, right? So Tn is equal to n, Tn by t is equal to n by 2, when 10 n by 4, it is n by 4, n by 8, n by 8, it till running n upon 2 to the power k, and then it will be terminated. What is the sum of this? So here is the series. You can see I'll take here the addition of all the numbers n, n plus 2, n plus 4, n plus 8, n upon 2 to the power k, 2k. I'll take the common 1 plus 1 upon 2, 1 upon What is this? This is basically the summation of 1 upon 2 to the power I is equal to 0 to k. What is this? This is basically the constant because it is 0 to k. So it is coming like a 1. So what is the complexity? Complexity is big O of n. Understood? Next, this is the another example you can do by yourself. You can just take t 3tn by 4 and theta n square. So what is this? Whenever tn is running, like I'll just show some steps like tn. So it is taking n square. So n square elements are processed, 3tn by 4. It is running. When it is running again, so in the place of n, you have to be right here n upon 4. So this is the way you can just at the end you have to be addition all the variations. Again, one more example, tn by 2 plus tn by 3 plus theta n. Master theorem. So the major problems are solved by the master theorem. What is master theorem? It is basically giving the three cases. So if a recurrence relation is in the form of this, Tn is equal to Atn upon b plus Fn, and there are some condition like A should be greater than, here you can see here the written A should be greater than equal to 1 and B must be greater than 1. That means it should be divided by the any number which is greater than 1. If the recurrence relation is in the form of this, then we have a three case. What is this? Case number 1, if Fn is equal to big O of n to the power log base Ba minus epsilon for some constant. What is the value of epsilon? It should be greater than 0. It never is 0. Then the solution is Tn is equal to theta of n log base Ba. Another is if Fn is equal to n log base Ba, then Tn is equal to theta n log base Ba log n. And the third case is if Fn is equal to n log base Ba plus epsilon for some constant epsilon is greater than 0. And the another condition. In the third case, you have to check the another conditions. Another is A into Fn upon B is less than equal to Cfn for C is less than 1. Got my point? So, for some constant, if the both conditions are true, then Tn is equal to theta of Fn. We'll check some, taken some examples. So, here you can see there are three examples here. First is Tn 9 Tn upon 3 plus n. Okay, I'll take an first example. So, in this example, you can see the value of A is 9 and B is 3 and Fn is, we can say that n. Okay, so A is equal to 9, B is equal to 3, Fn is equal to n. What is the value of n log base B? So, n log base B, that is n square, right? So, what was the condition? 2 and the Fn is n. So, the power should be minus something. We have to be minus something. And the minus 1 is minus 1. You can see here the first case. So, first case is true. For if I can put the value of epsilon is 1, then the first case is true here. So, you can see the case first is can be applied. So, what was the answer? Answer is like theta n log base B. Okay. So, here what is n log base B? That is n square. So, Tn is equal to theta of n square. Got my point? So, you can directly put the value in the master theorem and you can get the answer. Got my point? So, it is easy to solve any recurrence relation if any recurrence relation in the form of this Tn is equal to Atn upon B plus Fn. If a recurrence relation in this form, you can just calculate it n log base Ba. If the power is higher, you can apply the case number 1. If the power of both n is equal, you can apply the case number 2. If the power is lower, you can apply case number 3. But in the case number 3, you have to check the third one, the another condition, that is Afn upon B is less than equal to Cfn. Okay. Okay. So we already checked one example with the case number 1. Okay. Let me go to the case number 2. Okay. So Tn is equal to T2n upon 3 plus 1. So what is the value of A? A is 1. The condition is true. A must be greater than equal to 1. B is 3 by 2. It must be greater than 1. So it is greater than 1. It is basically the 1.5. And Fn is equal to 1. If I can calculate here n log base Ba, you can see here, if I can calculate this. So n log 3 2 base 3 by 2 base and the 1. So I think you must be know about it. If anyone any base for log 1 is always 0. Okay, so that means it is not basically 0, it is n to the power 0. It is not 0, it is by mistaken here written here, it is basically the n to the power 0, n to the power 0. Now we have to be check that. If I can compare this one f, so we have to be check fn is equal to big O of n to the power log base ba, right? So this is basically n to the power 0. And what is fn? Fn is 1. If I can multiply here n to the power 0, is there any effect of this? No, because n to the power 0 is 1, 1 multiplied by 1, 1. So the both side, if I can say check left hand side and the right hand side, both side the power of n is 0, same. So you can apply the second case. What is second case? Second case is that the answer is n log base ba log n. So n log base ba in this case, what is n to the power 0? That means nothing. And the Tn is equal to log n. Okay, got my point? Let's see the case number 3 here. So in this example, you can see a is equal to 3, b is equal to 4, fn is equal to n log n. Okay, so I am again calculating the same thing and n to the power 0.793. And here I can check here, n to the power is 1. So if I can see here, it is basically the less than. So you have to be add something. You have to be add something. If you are going to add something in this, so you can see it is basically equal. You can apply the case number 3 here. But in the case number 3, you have to be check the second condition. Second condition. Hence, you can see here the epsilon is 0.207. Now we have to check the another condition, that is a fn upon b is less than equal to c fn. Okay, so the value of a is 3, n by 4 log n by 4 is less than c n log n. Okay, so if I can check here, there is the value n to the n is crossing here, and if I can check, the above inequality is satisfied for c is equal to 3 by 4. If I can put here the value of c is 3 by 4, it is equal, right? Understood my point? So this is the 3 by 4, log n by 4, log n by 4. If I can put here 3 by 4, so it is less than. So the condition is satisfied. So you can apply here case number 3. Case number 3 is told us that if the case number 3 is satisfied, both conditions are satisfied for all the values, then Tn is equal to Fn. So Tn is equal to theta of Fn. Fn is n log n. So the solution is n log n. Got my point? So this is the way you can solve the problems in master theorem. Again, one more problem is here. Solve Tn is equal to 2Tn by 2 n log n. A is equal to 2, B is equal to 2, Fn is equal to n log n. If I can calculate it here n log n, so it is basically the n. Now we can compare with this n is to the Fn. Okay. So if you can see here the position is n and it is basically having at log n. So it is higher than. So we have to be add some value here in the power. That means it is maybe the less than or equal to the. Okay. Now you have to be check that second condition. Second condition is also satisfied. If you can see here, if I can apply here a plus epsilon, but if I can check the second condition is false. So clearly there does not exist any epsilon which satisfy the condition. There is no condition here to satisfy here. So you cannot apply the third case here. Okay. Got my point? So it never necessary that if the condition is one is satisfied, second one is not satisfied, you can apply a master theorem. You can apply any theorem. You can apply any cases, but before applying, you have to check the conditions here. Got my point? So these are some examples you can solve by yourself. You can just take a screenshot and put your solution in the chat box. Okay. Thank you so much.